I also modify a little bit about on the title of my talk. The title we find in our program is called Probing the Nanoscale Ice Adhesion Mechanics. And I changed to nanoscale de-icing by molecular dynamic simulation. De-icing means get rid of the ice. So this is more straightforward, more clear when you go through my slides with me. Ice. Ice is an interesting substance. We're now in Sicily, we're hot, so ice we use to make ice creams. But imagine the place where I'm working in Norway, especially in winter, you can expect excessive icing too much. Ice rolls, ice adheres to everything, to car windows and cause big trouble like these guys. These guys are working on a so-called high voltage tower. They connected the transmission line to get rid of the ice. So ice have lots of troubles. I will go through. In my outlines, you see the first part, I will talk about ice problem to further motivate my study again. And then we have ice. We need to study to get rid of the ice because it causes troubles. So I will follow up with what I do. It's basically atomistic modeling, and I use so-called molecular dynamic simulations or MD simulations for short as you might. And then also follow up with some of my results and small summary and some outlook. So ice, as I say, ice adhere to almost everything. And ice erodes is the most kind of a common problem to working on in a winter day. Normally people fall and get trouble and go to the hospital, which is not good. And in Norway, especially, there are lots of oil rigs offshore on the sea. And you can imagine in winter, there are lots of ice adhesion to the oil rigs, and then it cause trouble. Maybe the whole structure fall down. And this guy, when you look at here, this is not a tree, but basically it's the ice. Oh, sorry. So if you look at this guy, it's not a tree. This is actually the ice adhere onto the transmission line. It's so big and it's so heavy. In the end, everything falls down. Not good. And the problem, of course, in the formal terms, what we do, look at imagine the other guy there on the first slide. They use this very heavy axe to use brutal force to keep the ice off. This is called active de-icing, which is too costly and too tiresome. And the new era to get rid of the ice, to find another way, we call it passive de-icing, to find a way to make some surface that not like ice. We have the term called ice-forming. Basically, it's like hydrophobic. Hydrophobic is hate water, but ice-forming means hate ice. And if we can design this kind of surface, you imagine in the ice adhere, and the adhesion strength is so weak. Basically, by wind or by shaking, like we're shaking a tree, lots of water drop and the tree falls down, the water falls down. You can achieve that goal. We can also, it's ideal for solving the ice problems, but that is far. We need to go very long distance, and this is actually the first status of research in this area. I have tracked the program of this big conference. I'm the only one that study ice. I hope this is also very interesting to you guys as well. So, ice adhesion. Let's go first to understand the very fundamental way on the atomic level of ice adhesion. The main factors determines how ice adheres strong. But in this case, the adhesion science for ice is to weakening it. Normally, we make some glue. We want it to be stronger. When we attach something, we want it to be very strong. But in this way, we work in the other direction. But they are both not easy. And in an ideal case, I put it here, is very ambitious, very bold. We try to find something that is close to zero adhesion strength for ice. Again, this is ideal status, which is, again, far to go. And nowadays, we have some very preliminary knowledge about ice adhesion, like what is responsible for the ice adhesion strength, so to say. So I put some keywords here, which is one of the one is the surface energy, with this term that means a combination of chemistry, like electrostatic charge on the surface that can attract or form hydrogen bonding to the water molecule, ice molecule, so-called. So one of these factors for determining the ice adhesion is the surface energy, and of course the roughness, and many comes on. But there are so many. Let's start from the beginning. I will only choose one of them to study. And the other one, some people are very creative. Some great scientists. What they see here is to follow this idea. You go scale on the winter, then you find it under the ice skate blade and the ice. There's a small layer of water here, and this water turns out to be very important for reducing the ice adhesion. So my study very beginning, very amateur. So we start with building models, only study two factors. One is the surface energy. I built two surfaces. One is the silicon surface, which discussed the yellow one, and the other one is graphene. So the silicon have a stronger ice adhesion or water adhesion strength. So I have representatively to produce different energy attraction level for ice to sit on. And also further, I put a small layer of water molecule. You see here these guys, this yellow guy, this red and reddish and I one there, and the water and the ice small cube sit on top of it. And then I do some simulations. And in this simulation, because we're trying to understand the mechanics to determine the ice adhesion strength factors, or to get rid of the ice. We can pull the ice. In this case, you pull the ice up. This ice cube here is very small. One edge is 8 nanometer more or less. And also we can shear it to determine the shearing strength. And again, this is very preliminary study. We are going for a further one in that outlook. But let's start from this very smooth surface and do this simulation to detect or to understand how ice adhere. And what I do? Pooling, in this case, we look at the other experimental method that what Professor He has shown, like nano-indentation, also to study nanomechanical problems. But in this case, we can also mimic other experimental setup, like the atomic force microscope. You see here, this is the very tiny so-called anti-level, or the small tip of the experiment, small head. They pick out something very small from the surface. In this case, you see this pick up some proteins. And then in this case, this cantilever that move up and then pull things away. And in my simulation, it's also similar. I play a harmonic potential onto the ice. Or this is actually ice. I color it in the wrong way. And then the force. You imagine this harmonic spring is in here, and then you moving out slowly. And they say the force keep loading on the surface. At some point, if the force is big enough, the ice will be tilted apart. And also you can pull in this way, as I saw in the almost sliding schematic drawing. And here is, let's see what happened, as I already described. So during the loading of the force keep loading on it, and at some point, this ice, although it's ice, it's cold, but it's still vibrating because it's thermal fluctuation. At some point, some small gap open here, and the ice cube rip apart very fast. If you look at the force profile during this process, you can observe very brutal detector, like what the organ see from the last assignment you see. At the very beginning, this guy sitting there happily, so the force keep loading. And at the very point, this force drop dramatically. This is kind of a sudden drop, and this signature of this detection event. I have a movie at the very end of my slide, so be patient. We will be there. And by doing this, because we have the force, you can reproduce this simulation many times and grab the average force or the force that you need in this kind of to detect the force. And then somehow you have this area of the contact area, you can somehow estimate how much detaching stress you have. And in this way, it's a measurement of how strong this ice adhere on the surface. And of course, we can also put the water drop there. Let's compare so now here we're looking at the ice on the graphene already. So the graphene is, as I say, have a lower ice adhesion friendliness than the silicon. You compare the tip force here, this is around 13 nanonewton, but you compare, let's go back to the last slide, around 22, 23. So we already, the ice adhesion strength already dropped a lot. But if we put further the water layer down there, it reduces the ice adhesion even further. And of course, it's by intuitive. It is the water swimming or vibrating even further, like stronger or more violently than the ice. So in some nano cracking may happen here because of the ice moving here. So this is promote the detaching event at lower forces. So the water layer somehow like enhance the nano cracking initiation, if you like. And of course in shear. So the shearing force is like this. I put 4 systems here. I hope you still remember the system. IS, S is silicon, ice is ice, so it's the ice on the silicon, which is the black line. The adhesion strength is so strong, the ice is actually hopping in you. If you put the force, shearing force on it, and if you put the water underneath, some of this hopping, some of smooth out. And if you're comparing the lower energies, the surface lower surface energy, the shearing stress is even reduced dramatically. If you're comparing the peak force to here, is to all the magnitude, and this ice, this adhesion energy surface is, of course, is higher than the graphene, as I mentioned. But the water layer on this case is also have the same effect. You can see the blue line, which is not very clear here, is also reduce the shearing stress. And the shearing stress by taking this the force that observed during the simulation and normalized by the contact area. So not much to show because the result is quite preliminary, as I say, and my summary is also short. So what I want to show here, as ice is the only one in this very big conference, which is my not, of course, it's not in the mainstream. So what I do during simulation of ice, which is a very urgent need for people in the north. Actually, ice problem is not only a problem in Norway. The picture that you saw here is actually a picture taken in China. So I believe that ice problem have many countries in Europe have this problem, and also other countries like the US, China, Japan, Korea, they have big problems. So ice, to understand what is responsible for ice adhesion, and then find a way to conducting ice, this is the right way we have to study, put our research strength on it. And what I show you, I studied two surfaces now. One is the factor. One of the factor is the surface energy. Later on, we're going to go to make the surface more complicated, have some nano topography, then understand how ice adhesion affects nano topography. And then also we're going to study maybe further on to understand the water layer, how this water layer thickness or dynamics can affect the ice adhesion too. And before I go back to finish, I would like to show you a movie. Could you please play the movie? I need to play it twice. So here, so the example we saw here, this is the ice graphene surface, this is the ice, all the water, so to say. So you can imagine the spring is loading here. So the force is pulling high and high at some point. Could you play it again? And I will shut up and let you enjoy the lovely movie. Could you play it again? Yeah. This is like small legs, actually, like small animal legs. And here we go. Yes, it's one of the simulation movies. And can you go back to the slides again? Thank you. The very last one. The very last one. The last one. The last one. There's no one. No, the final one. Yeah, exactly. So this is where I work as again. So the NTNU nanomechanical lab. We're not interested in this very tiny, teeny size mechanical problem. We're also interested in bigger scale. So we have multi-scale research team in this lab. And this lab is led by two professors, Professor Liang Zhang and our chair, Professor Jing He. And yes, I'm now happy to take a question.
Thank you.